Again, thank you for inviting me. My name is Nicoleta Cristea. I'm a research hydrologist and data science fellow at the University of Washington eScience Institute. I am working together with other researchers on this project. Their names are Jensen Sun. Jensen is a research professor at George Mason University. Anthony Arendt and Scott Henderson are data scientists and research scientists at the University of Washington eScience Institute. Maureen Denal is an assistant professor in Earth and Space Science at the University of Washington. And Annie Burgess is ECIP lab director that is helping us with various tasks. The purpose of this talk today is really to share from our experience with this project that we're running that's called GeoSmart. And what is GeoSmart? GeoSmart is an educational framework dedicated to advancing machine learning adoption in the geosciences. The current focus is on hydrology, seismology, and cryosphere, but we are expanding and hopefully we will include other domains as well. And I would like to thank you for making space for me to show you this and hoping that you'll be interested in our activities. What are our goals? Our goals are that any geoscientist can access, learn from, and reuse GeoSmart training materials. And for that, we have a website dedicated to hosting various materials that are educational in this direction. GeoSmart is aiming to increase the number of geoscientists who are able to more easily and confidently apply machine learning appropriately to their own research. And also, GeoSmart is aiming to help develop an inclusive research workforce capable of advancing fundamental geoscience challenges through broad adoption of machine learning. And I'm going to click on this link. If you could tell me if this link takes you to the site, and you see the site.
Yep.
Okay, excellent. Because we'll be talking and going back and forth between the slides and the website. And you see at the top of the page here, there are different tabs. And I'm going to click on those sequentially and walk you through the content of our site. So any geoscientist can access, like we've made sure we have a website. Now we're putting stuff and making it available. Thank you for sharing the link. All right, what do we have? To accomplish these goals, we have funding from National Science Foundation. We have support from the eScience Institute. The eScience Institute is a data science hub aiming to advance data-driven discoveries in all fields, while ECIP is the Earth Science Information Partners. It is an umbrella organization that's helping geoscientists with data and other needs. How do we do it? Really, our approach is three-faceted. We are aiming to develop a class curriculum. We're aiming to develop use cases and machine learning workflows that are end-to-end projects using machine learning that can illustrate a use case completely, so the learners can get an understanding of what can be accomplished with machine learning. And the other side of the things are community development. And how we're doing this is with immersive hands-on learning during Code Weeks or Hack Week events that we are hosting at University of Washington eScience Institute. So I would like to go back to the website, and I'm gonna click on this link. But really, if you go back to the main website, this content is under curriculum. And if you click on curriculum, we do have a class curriculum vision, what we think it's needed to provide the basics for applying machine learning and a good understanding of how to use machine learning in the geosciences. As I said, this is at the moment illustrating use cases in seismology, but really the goal is to include other domains. And if we click here on this link, this is taking us to an open curriculum that has a little bit of background where it's being taught at the University of Washington in Earth and Space Science Department. It is a 400, 500 level class, which means that it has undergrad and graduate students learning about machine learning and data science tools. There is also a student version of this Jupyter book that is without the professor or the instructor responses to specific questions. This site includes our learning objectives, demonstrate computing skills, or like not acquiring computing skills in using Pythons and Jupyter books, version control, and other things. Develop and apply machine learning workflows, including data preparation, model design, and training, validation, and evaluation, as we heard about all those steps this morning. Describe and demonstrate the adoption of open science principles, which goes a little bit beyond the use of machine learning, but also making the code available as open source, and also thinking about reproducibility and how we'd like to share our code and results with the broader audience. Some prerequisites and so on. Okay, so if we go on the left side of the screen and clicking through these links in our Jupyter book, we discover the entire content of the class with like introduction to the Python ecosystem, into the computing environment, in this case, a Jupyter environment, Jupyter Lab, a bit of what's Markdown and code blocks and other things that we typically use in Jupyter hubs. Also, because the class has project work and collaborative work, we are learning about version control and GitHub and how to manage the code development and how to potentially reproduce things at the end. We learn about computing environments because machine learning projects could be data intensive. We have a bit on the high performance computing, cloud, and other available resources that could or could not come for free, such as Google Colab or AWS platforms, and also Azure. Then the next thing is data manipulation, and we do have some bits on the types of data and formats, and also how to handle the data with NumPy arrays, and then moving on to pandas and X-arrays and other things that are important for data manipulation for machine learning, especially in how to, for example, reduce the data set if it's too big, but still relevant for machine learning input. And then there's on feature engineering and transformations of the data that could feed in machine learning models. And then in the end, the goal is to have a data set that's machine learning ready. So we go through all these steps in chapter 2, while chapter 3 now starts with the actual machine learning techniques. And we have some examples for clustering, the unsupervised type of machine learning, and then classification and regression, more binary classification, logistic regression, that's not really a regression, but a classification method, and also other things like decision trees and so on, until we get to chapter 4, that is deep learning and introduction to neural networks and perceptrons and like convolutional neural networks, and then the recurrent neural networks and some other things too. We have a little bit on model workflow and machine learning reproducibility at the end. And that's in a nutshell the content that now it's available online. And of course, this is a class, but it's really for everybody who'd like to peruse it and learn from it. That would be the class curriculum part. This class has been taught for the first time in the fall of last year. This year, it will be revisited. The content will be revisited, and it will be taught again. And these are a couple of slides that the instructor put together to give some feedback on her experience when teaching this class. This class was taught by Maureen Denal in Earth and Space Science. And the way we thought about this was that students could learn about data science and machine learning as tools to address geoscientific problems and not develop, not tweak the models or the theory, or not learn about the theory of the machine learning, but more about the application side of things. And so that's why we also included things like open science and ethics and practices. Data structure, statistical learning, machine learning, and other computing skills. The structure of this class was 3 times per week, 1.5 hours lectures and in-class computing exercises. The tutorials, as I showed you, were mostly notebooks with cells already prepared. Introduce a 30-minute lecture style concept about the different algorithms to build intuition into how to use the models. And then something like 30 minutes, a tutorial on how to use the various tools. And student-led or group exercise to apply the tools on other data sets. The graduate students also had some reading assignments that are more complex than simple use cases taught in class. There were a couple of homeworks that students reported that these were extremely useful to apply the concepts learned in class. And really what I mentioned earlier, that we'd like to expand on the geoscience discipline and include more types of data sets and science applications. The class also had a final project, and sometimes a grad student was paired with an undergrad to build an end-to-end machine learning workflow. There were some technical challenges related to how you teach this type of class. The UW IT provided a Jupyter Hub for the class, but there's technical considerations to think about. For example, considering a minimal set of containers with easy pip install packages in each of the containers for each of the demonstrations, or perhaps a group of demonstrations in the class. Also, other things to consider would be to use Google Colab. But again, there could be some other technical issues to consider. And this is a work in progress. We will involve expert reviews to increase the quality of materials and expand to other domains. One thing that we talked about was if we wanted to, the content is open, as you've seen, if we wanted to, make this available as a hybrid course or something similar outside the University of Washington. And these are a couple of examples that I'm pretty sure you're familiar with. The Boulder course on data analytics and is an online certificate. There's another course at Brown University on machine learning, but not open. Other things are happening at the Brent School as a Master of Environmental Data Science. So now I'd like to use the website again to talk about our use cases. I'm going to go back to our main website and click on this tab here. And this website really hosts examples of machine learning examples in the geosciences. How did we come up with this content? Two ways. One was from our ongoing research. If we had a machine learning related project, we would put all the code together and we make a tutorial, and we will include it in a Jupyter book format, and then we will publish the book. The other way we built these use cases was through a partnership with the Earth Science Information Partners that I mentioned earlier. And we put a request for proposals online perhaps a year ago, asking for something similar, like if your group or other groups that you knew of had some publication out with a machine learning model that they would like to share and showcase on our website, or that's one thing, or if they wanted to develop one from scratch, that was also possible. And we did form a cohort of about 20 people that we followed with for about 6 months into their development of these use cases. And now we're almost at the completion of these books. We have maybe 5 now, and 2 more are completed but not integrated into books. But what these books contain? And I'm going to click on this one and show you as an example one that came out of our research on using machine learning for remote sensing applications. In this particular example, it was using random forests to identify snow in PlanetScope imagery from planet. And so we put all the content that we had, and we just published a paper on this that just came out in one of the Frontiers journals. But all the analysis that was done in the paper, we put in as a tutorial. And so if we do start with this structure, we would find a motivation for why we chose to apply machine learning. In this case, it was that PlanetScope imagery did not have a shortwave infrared band, so we thought that a better approach would be to use the visible band and the near infrared band the planet has in a machine learning model to identify snow. That was our primary motivation for why we chose this particular approach. In chapter 2, we detailed the tools, and we've learned this morning about scikit-learn and how to use it. This example also uses scikit-learn. Then we have the big thing, that's the data preparation, how to handle the data to make a machine learning ready data set, then how to use it in the model, how to tweak the model, the number of trees, the tree depth, all other parameters, and then a bit on model training, how to split the data into training and testing subsets, how to define the model. And then in the end, it was performance evaluation and also applying the model on a different data set. That's an example from one of our current projects, but I would also want to illustrate an example from the ESIP cohort that it's completed, I think. This tutorial is supposed to run on Microsoft Planetary Computer, and it is about predicting snow water equivalent globally using downscaled CMIP6 data. and it's going again. You see that there's a slightly different structure in the use case template, but still like available notebooks that anyone can use. If you go here to the repository and clone it on Microsoft Planetary Computer, we expect it to run. So again, on background and data preparation, how things are being put together. In chapter 2, it is about implementing the model and training pipeline. In this case, the approach was a recurrent type of neural networks, LSTMs, that were identified as working well with time series. And this is how things were put together here. A little bit about the background of LSTM networks, and then some quick checks on the data quality, and then how we train, and then in the end, how we evaluate the data. So these are some examples that I showcased for you today. There's a lot more. If you'd be interested to browse them. Also, we do have a section here about contributing content. If you are interested in contributing, or you know somebody who is and has a GitHub account ready, we do have these two types of templates, Jupyter book templates that I showed you before, available, and either you or you can ask us to integrate all the content and make it like our story, right? I think I see these books as our data story about machine learning and machine learning applications in the geosciences. You can please interrupt me whenever I don't see you at the moment, but please interrupt me if you have questions or anything that I can explain further. All right. Our use case library. We envision these use cases as demonstrating end-to-end workflows for self-paced learning. And also these use cases could be a starting point for learners that provides motivation for what can be accomplished, and also can serve as examples for class projects and what it is expected as an end product in the class. All right. Next, I would like to go back on our website and click on this Tools tab. The Tools tab and this Tools website hosts some links to some tools that are being developed as a side project. This one in particular, it's called GeoWeaver. It is an open source productivity tool for managing fair machine learning workflows. Jensen Sun, our collaborator, is leading a NASA-funded project to develop this open source workflow management tool that saves the history of the ML model runs together with the source code. And so everything is packaged at the end into a zip file that can be shared with others. And that is, in his words, using GeoWeaver as a long-term investment and will make every scientist's work fresh, preserved, and understandable even years after the original experiments. If you are curious to hear about more about GeoWeaver, you can contact Jensen Sun. But there's also some links here to his website that hosts a live demonstration on how to use GeoWeaver here. And also this is a link to his GitHub account that hosts GeoWeaver that was initially an ESIB lab incubator project. The other thing that we're hosting here is one of our one group that was part of our ESIB cohort developed an open source tool, which is like really a Python package for Gaussian processes for interpolation and simulation. It is called GeoStatsPy. It was also recently published and has, if you click here, it will take you to their GitHub account where you can read more and about how to apply it. They also have demo Jupyter tutorials and other things that can help with adoption of their tools. Many of the Kriging and Gaussian interpolation tools were, as far as I know, were implemented in large GIS software packages before. This one in particular is open source and hosted on GitHub for everybody to use. If you click here, it will take you into a binarized environment where you can play with the tool as described on the GitHub account and by the authors of this. We're hosting these two different projects as tools because we do think that they have potential for broader adoption, and we, of course, would like them to be used widely. All right. In development, there is an open source tools for labeling remote sensing data, but that's not finalized yet. Once it's ready, we will feature it on our website as well. All right. These are the people who contributed to the development of the use cases. In total, about 20 people. The Microsoft Planetary Computer example that I showed you was developed by Andrew Bennett, who is just a newly minted assistant professor at the University of Arizona. And I would like to thank him for his contribution and to others as well. What has been covered through these use cases were classification and regression and clustering problems, using different approaches ranging from simple linear regression to Gaussian processes, decision trees, other types of clustering algorithms such as DBScan, and also deep learning in various shapes. The packages that were covered include scikit-learn, PyTorch, TensorFlow, Keras, SciPy, QML, and LightGBM. And you can learn more if you're curious about how these packages were used for some particular use cases that a group had covered on the website that I showed you. All right, and then now we're perhaps getting closer to finalizing the description of our approach. The last bit is community development and how we're doing this. Perhaps you have heard that eScience Institute is organizing Hack Weeks. What are these Hack Weeks? If we click on this link, this lands a splash page for our upcoming GeoSmart Hack Week, which is gonna take place at the end of October 23rd to 27th in Seattle. It doesn't have that much content at this point, but if you are curious to learn about the Hack Weeks, you can click on this red button, and that takes you to our University of Washington eScience Institute Hack Week page that documents what Hack Weeks are about. Hack Week missions, creating communities that have a sense, that foster a sense of belonging, and aimed to educate people through immersive learning and hands-on project development. We believe in co-creation of materials and open source. This event allows for networking and learning and working together and on GitHub, and ideally in person. We do have some more information about how Hack Weeks can serve different communities, providing data science education in different fields, and also expanding data science accessibility to underrepresented individuals through a culture change of openness, cooperation, and kindness. We believe in creating community software, and sometimes really nice packages can be developed, followed a project at a Hack Week, or advancing science in different shapes. So that's the mission of our Hack Weeks. And for our GeoSmart program, we would like to organize 2 Hack Weeks. The first one is going to be, as I said, in October. The next one, perhaps early next year. But sometimes there's not a need for a Hack Week. And these are some alternatives to consider. We do believe that for GeoSmart, hands-on learning is really important. And as part of our program, we have scheduled 2 events, 2 Hack Week events. Traditionally, how the Hack Weeks were designed, or really in the mornings, there were tutorials. They were still hands-on, or maybe more hands-on. Some of them were more hands-on, some of them were less hands-on. But there was a person, an instructor, a tutorial lead in the morning, presenting a topic or a package. There will be 2 each morning, and then in the afternoon, groups would form. There'll be project pitching, and then if people would find their interests, they will join a particular group and will work together on a specific problem during the afternoon. And then at the end of the week, they will report on their findings. And this is an example, a group that was happily working on their project during Water Hack Week 2019. But for GeoSmart, maybe this approach could be envisioned to go either towards more tutorials, we thought, or either towards more hands-on work. And we discussed these alternatives in our meetings, and I think in the end, we decided to hold a workshop that would inform our upcoming Hack Week. I'm going to return to these slides. And this workshop took place not too long ago, May 8, 9, and had specific objectives, really identifying community needs. Where are the challenge points? Like, what do we want to teach? How do you approach a hands-on event like that? And create learning outcomes. Like, what do we want our participants to learn? One of the questions we had was where they're at with their skills. Like, have they experimented at all with machine learning? Do they know how to handle data sets, big and small? Where do we start given the wide range of participants and topics? And then there were questions about technical infrastructure. What tools do we need to have in place for participants to effectively work with data sets? And in terms of community building, do we have a strategy for fostering a machine learning community of practice for the geosciences? And so we did put out a survey. And if you click on this link, you will get to see what we asked in preparation for this workshop. And I would like to take perhaps 5 minutes. I don't know how much I have in total, maybe 20 at this point, maybe 15 minutes total.
Yeah, about 20.
I mean, if you're interested, I invite you to take a look at the survey and enter your responses for 5 minutes. Think about what we asked and what would you do if you were to run a GeoSmart Hack Week. And I think in 5 minutes, we will get back together and discuss your opinions and your answers. Would that work? We will consider your responses in our future evaluations of this survey, but we did circulate the survey at the University of Washington, mostly a little bit outside, prior to our workshop, and 45 people responded to our survey. And I would like to walk you through some of their responses, and also thinking about your responses, and maybe you would like to comment on how well or like what's different from what they had to say. In terms of career position, people who are interested in this were mostly PhD students, postdocs, but also professional scientists and academic researchers. And that the general level of interest in using machine learning was relatively high. I'm hoping you have a strong interest in this too. But feel free to comment on any of these slides. And this one is about your machine learning training needs for geoscience applications. This is what came out of the 45 people survey, that machine learning for large data sets and cloud computing are important. Then machine learning for time series prediction, pattern recognition, and other applications they would also like to learn about for remote sensing and some parameter extraction or model tuning. Is that something that resonates with you, or what are your training needs, or like your students' training needs? What do you think is missing here?
I think one of the things I might have put, and I can't remember all the different options, but some of those definitely aligned with things for me. But then I was trying to think about ways to include some of these things within other coursework that's not necessarily just machine learning as a whole, right? So, I can imagine a data analysis class that then is then a machine learning data analysis class that'd be really interesting. But I don't always have the time to dedicate for that. But would love to incorporate in a, say, remote sensing class, and how can we use machine learning within remote sensing so it's maybe just a small segment that's not going into all the details, but as a way to show it out kind of in the real world, I think would be a really interesting thing that I'm interested in various ways. So.
Thank you. That's helpful. I think that the real world stuff is interesting. I mean, interests me too, and that's why I'm very keen about those use cases, because those were supposed to be real world use cases, right? From publications, like that can become applications or tools. There's some other thoughts that the participants to our survey put in the box that was provided broad perspective on machine learning philosophies and strategies for representation. That's a broad thing to include. Connection to information theory, model data integration, uncertainty quantification. That's really important to reference data sets. That's something that we are interested in for the educational content. As I said, we do have some data sets, but we are interested in collecting more curated and relatively small data sets that we can use in our classrooms, because I think I detailed some of the challenges in teaching how to do machine learning on big data. Cloud computing may be necessary. We don't have all the building blocks quite yet in place, but we're planning to put in at least 2 tutorials that will exemplify how to use big data on AWS and Azure in the future. There's other things like that are really important for where the science is going, such as physics informed and or physics constrained ML, that we would have to at least have one use case referring to that type of application. ML being more generally understandable, like generalizable. I think I read something about big models in the geosciences that were supposed to do everything. I'd still have to try them and see if they really do everything. But maybe the field is going there. ML for data fusion, that's important also for remote sensing. ML for image raster and super resolution. One other thing that we asked was, what is your current level of machine learning knowledge? This group in particular was pretty informed about the topic. Most of the responses were, I have used machine learning for research. Some implemented some algorithm themselves. Little to no exposure was not really. So I think that the machine learning applications are taking off, like we heard this morning too. And there's a lot of people that like started with little to no experience perhaps a few years ago, but now everybody got to use at least scikit-learn in some way. If you have used machine learning, what are the most common tools you have experience with? Again, scikit-learn, and then all these other tools like PyTorch and TensorFlow, Keras, AutoML, and PyCaret. These are some newer packages that are available. When you think about machine learning, what do you feel like you need most help with? Not surprisingly, workflow management and reproducibility. Not surprisingly, computational environment managing, right? Computational environments and use of GPUs, model selection, gaining insights on how to work with deep learning models, and preparing training data sets. But it's interesting that I think this group at least has passed this challenge of preparing data sets and perhaps little, and now is ready to make the workflow available and reproducible, and also perhaps run things on GPUs and cloud. What they had to say was that in addition to what was asked, that adapting machine learning architectures and methods to specific problem domains, life cycle management. One thing that came up was the interoperability between machine learning routines and other models. I think this is really important. One other thing that's not here perhaps is data standards for machine learning and fair data sets. I believe I could improve my machine learning workflows to be more interpretable and computationally efficient. I know the theory, but never personally build a model that does anything actually useful for my work. So, yeah. And then we asked, what was your preferred mode of community building and learning? Because we thought about this upcoming Hack Week. Now we are in a virtual event, like hybrid. I wish I'd be in person, but a lot of other people, when asked, preferred having the option to be virtual. I think that in the end, we will have it an in-person only event, but I think that really things changed and hybrid events are also very desirable.
Yeah, I think one of the, just to comment on that, because I ended up choosing the hybrid event, even though I don't fully enjoy hybrid events, but it's the ability, in case I can't travel because of a busy schedule, that allows more opportunity to potentially participate in some of these things. That is that thing, but it is definitely a non-zero factor in organizing and pulling off a hybrid event, as I'm sitting next here to Nicole, who was the savior in doing it for this one. So
it is very hard. I agree. We did it over the pandemic and it was terrible, but it's something to consider, as you said. Yes, I think we're leaning towards more in person, but like based on the results is really something to consider. We also asked about the duration. What would work best, like short and intensive, like the Hack Week type of thing that we discussed earlier, virtual meetings spread over multiple months, or a webinar series. In the past, we did have like a quarter-long webinar series that we organized with Quasi, but short and intensive seems to be the way for this event, at least. And again, this is the upcoming event that we're preparing. We talked about it. Based of these results, really, we're leaning towards fewer tutorials and more project work. And at the workshop, we discussed potential projects. So we were thinking like putting together maybe the data sets, or at least some data sets that are in the machine learning ready, and then the participants have a better chance of playing with the model rather than handling the data sets at the event. And so they will not start necessarily from scratch, as we did with the other Hack Weeks, where everybody was fresh and arriving at the Hack Week and started everything anew. In this approach, we would pre-form the projects. There'll be a GitHub account already. If somebody wants to start a new project, they'll have the opportunity to do so, but there'll be some prepared projects that they could just join. At least at the workshop, we identified that that's perhaps the best way to go with this particular Hack Week. And we're testing this model as we go. But I think that's what's going to happen, because the Hack Week projects are the primary tools for immersive learning. They're hands-on and so on. And if you'd like to hear more or see more, can go on our YouTube channel and see how things happen. Before the event, we start the project ideation and team formation. We will work on our projects during the event. Then after the event, some of the projects do evolve into scientific papers, Python packages, tools, whatever. Some just don't evolve at all. But there could be some really surprising and useful outcomes. We have a draft schedule, but even though we do have a draft schedule that looks busy, I think at this point we're just considering an hour of presenting common workflows for machine learning, a little bit on GeoWeaver on reproducibility and management, computing resources, ethics, and leave the people do their work. And I think I could talk more, but I don't have time. I would love to hear your feedback, but I also not sure if we have time. I'm just gonna stop share now. And thank you for listening to me.
Yeah, thank you so much.
Thanks.
We may have time for one quick question.
I'll ask one question if you can hear me.
I can't hear you.
Okay. For that class at the University of Washington that had a mix of graduate students and undergraduate students, I know it was geoscience, but was it a particular major or program, or just really broadly all sorts of different geoscience students were in that
It
class?
was with a seismology focus.
Okay.
But everybody can join. Like that's now our next step is to diversify the data sets and the applications. That was our first iteration of the class, but we're really looking into branching out to other fields. And also, like, we have a structure now. Professors that are interested in teaching this class can go there and take some content or inspiration and develop whatever they think it's useful for their class. But that was our goal, to make everything available and make everybody be more happy with their machine learning.
All right. Thanks.
Excellent. Thank you so much, and thank you, Stephen, for your question. I think with that.
Max has
That's a question.
Oh, sorry.
So this is a really great resource. This looks like something that'll be great for the community, and all the outreach you're doing is really neat. Have you been interacting with some of the other projects sort of related to this space? Mainly thinking like the environmental data science book out of I forget what specific group. But like the environmental data science book, I saw like some references to Project Pythia and that sort of thing. How are you like collaborating with some of those other groups, or trying to find like gaps or find ways to help collaborate across there?
That's an excellent idea, and we don't have a series of meetings to collaborate. We know of each other, I think. And I really made the Project Pythia content available, linked our use cases to the Project Pythia, because our goal is not to teach Python or data handling, but how to use machine learning. And I would love to get in touch with somebody that could, integrate these resources better into our content. So far, we only have links to this site. It's just, if you want to try X-ray, go on Project Pythia and try one of their cookbooks, But we'd like to make this more, to grow together in a sense, right? To be more a closer collaboration. And I'd be happy to talk with anybody that would be interested in working on, like, looking at the content and saying, well, if you want to accomplish this step, you really have to go on Project Pythia website and run this example so you'd understand how to use X-ray to generate machine learning ready data. I think this bit is missing, and you're right, it is missing, because we've been working in our own silos, so to speak. We do, like, I did see the Project Pythia presentation at IGU, but didn't really interact with anybody there. And I'd be happy to.